So here we go in problem sequence 4. We have acetic acid. Acetic acid is HC2H3O2, mixing it with sodium hydroxide. So we're adding sodium hydroxide NaOH. When we do, we get sodium acetate and water. Okay, so we need to find the excess reactant. To do that, just pulling up the calculator here on the side. To get the excess reactant, we need to find moles of acetic acid. So that would be 0.06 liters times 0.2 moles per liter. So you see where I got those numbers. 0.2 is right here. 60 milliliters is 0.06 liters. So 0.06 liters times 0.2 is 0.012 moles. All right, over here we got 20 milliliters of 0.2 molar solution of sodium hydroxide, so it would be 0.02 liters times 0.2 moles per liter. 0.02 times 0.2 is 0.004 moles. Since this is a 1-to-1 mole ratio, and I didn't leave a lot of room to work, I'm going to assume that you can realize that 0.004 is less than 0.012, and they react one of this with one of that. So therefore, I'm going to need, in order to make this go away, I need 0.004 moles of sodium acetate, or excuse me, of acetic acid. Do I have that many moles? Yes, because I've got 0.012, don't I? Okay, so what's the excess reactant? It would be the acetic acid, because I have way more of that than I need. And by that I mean, again, if I were to use all of the sodium hydroxide, given the 1-to-1 ratio, I'm going to need to have 0.004 moles of that. Well, it turns out that I actually have 0.012 moles. So that's more than I need, so that's extra. How many moles of excess reactant are present? Well, I needed 0.004, so I use up 0.004 to react with the sodium hydroxide. So I had 0.012 minus 0.004 will give me 0.008 moles of excess reactant. Moles of salt produced. Now this is the salt that's produced. There's also a 1-to-1 ratio with the limiting reactant. The limiting reactant was sodium hydroxide. So there's a 1-to-1 ratio in that limiting with the limiting reactant. So since it's a 1-to-1, there'd be 0.004 moles of salt produced. What's that concentration of that salt? So what is the concentration of the salt? Use total volume. So what was the total volume? Had 60 milliliters and 20 milliliters, so we have 80 milliliters total volume. To find molarity, you're going to need to take the moles of salt produced, which is 0.004, and divide by the total volume, which is 0.08 liters. Okay, now I'm back up just a minute. So we know that since 0.004 was limiting, that we will have, in a 1-to-1 ratio, 0.004 moles of salt produced. So that number there, moles of salt produced, was that answer right there. After we find the moles of salt, and we want to find its concentration, we need to divide the moles by the total volume in the solution. So it would be 0.004 divided by 0.08. And that's equal to 0.05. So that is the concentration of the salt, 0.05 molar. So this answer is 0.05 molar. Okay, the concentration of the reactant that remains. Well, what remained? The reactant that remained, what are the reactants? Reactants are acetic acid and sodium hydroxide. Didn't we find earlier that we had 0.008 moles of extra unreacted acetic acid, because we used 0.004, but I started with 0.012, The difference is 0.008 left over. So to find that, concentration is 0.008, again, divided by the total volume of the solution. So 0.008 moles divided by 0.08. So that's going to be 0.1 moles per liter. All right, so that's 0.1 molar. Now we want to know the pH of the solution. Okay, so what was the extra reactant? The excess was acetic acid. Is that a strong or a weak acid? So you should have thought to yourself, it's weak. So HC2, H3, O2 plus water makes hydronium ions and acetate ions. We know that the original concentration of this is 0.1. Since it's weak, you need to ice it. So that's initial, change, and then equilibrium concentrations. So we know that this is going to, some of this is going to react. We don't know how much. And we know at equilibrium we'd have 0.1 minus X. Initially we don't have any of this, but we do have some of this, 0.05 moles per liter to be exact. Because the salt that was produced up here, sodium acetate, when it dissolves, it does this. So if this is 0.05, that all goes away because it's soluble. Oops. So all we have left is the Na plus and the acetate ion, both of which are 0.05, since all of this turns into these things, and it's all 1-to-1 ratios. So the sodium doesn't matter because it's not in this equation, but the acetate is. That's a common ion. Remember the ions in common we talked about in class. So we start with 0.05 of the acetate ion. We know that if X amount of this reacts, we're going to get some of this and some of that. So at equilibrium, we'd have X amount of the hydronium, but we'd have 0.05 plus X of the acetate. So you know the equilibrium constant is Ka is equal to the hydronium multiplied by the acetate divided by the acid, just products divided by reactants. We know that this number from earlier in the test is 1.75 times 10 to the negative fifth. That's going to equal X times 0.05 plus X. On the bottom, you'd have 0.1 minus X. So if I change this into scientific notation, the exponent is -1. The difference between -1 and -5 is 4, so it's okay to ignore this X. So instead of saying 0.1 minus X, whoops, I'm going to say it's just 0.1. All right, and over here, since that's 5 times 10 to the negative second, -2 to -5 is 3 or more, so I can ignore this X as well. So now, just to solve the question, I have 1.75 times 10 to the negative fifth is equal to X times 0.05 divided by 0.1. Which is 1.75 times 10 to the negative fifth equal to X times 0.05 divided by 0.1 is actually equal to 0.5. So now to solve for X, divide both sides by 0.5. X is equal to 1.75 times 10 to the negative fifth divided by 0.5, so it'll be 3.5 times 10 to the negative fifth. And we want to know the pH of it. So since X is the hydronium ion, if I take the negative logarithm of that number, I have 4.46. So that number is 4.46. I think it's worth mentioning that since we have this sodium acetate produced, that would have shifted the equilibrium back this way, lowering this, which is why the pH is higher than you might expect for an acetic acid solution. Because when the acetate pushes the equilibrium back to the left. All right, now we're ready for the last little set of questions. Other than, well, I'm going to go ahead and talk about this. We haven't really done this yet. This is a lab on coming up on Thursday. So what we have, you remember the burette that I had in class. It has sodium hydroxide in it. So in this case, we're starting, this is hydrochloric acid, and this is acetic acid. You know the curve of the strong acid is the one that has a lower pH initially, because strong acids would have a lower pH, generally speaking. And the weak acid would have the higher pH. Okay, now the equivalence point, remember back a minute ago when we were doing the neutralization question right here? The equivalence point is the point at which all of one of the other, both of these are gone. In other words, you've reacted all of this and you've added enough HCl to make it all go away. So in this case, that would have been 0.008 moles. Okay, so when I've added enough volume of HCl to make 0.008 moles, that would match the 0.008 moles of sodium hydroxide. So they neutralize each other. They are both gone completely. On these graphs, the neutralization point is in the middle of the steepest curve. So about there on that one, and right about here on this one. Okay, so this is the weak acid. This is the strong acid. So the pH for the strong acid is about 7, which is what you would expect, because if you're titrating sodium hydroxide against hydrochloric acid, your salt that's produced is going to be NaCl. And NaCl comes from a strong base and a strong acid, so you'd expect a neutral pH. There's no hydrolysis. In this case, the salt will be sodium acetate. All right, now, and by the way, it doesn't tell us that we have HCl and acetic acid here. I just used those as examples. So if it was a weak acid like acetic acid, then the pH is around 9. So the base from which the sodium acetate originated would be sodium hydroxide. And the acid from which sodium acetate would originate would be C2H3O2. So it's a strong base and a weak acid. So the salt will be basic, which is at the point where both the acid and the base have been consumed. All you have at this point is the salt, and the pH, you see, is 9, which is a basic pH. How do the concentrations of the two acids compare if 30 milliliters of each is titrated with the same concentration of base? Did you notice that it takes the same amount of base to neutralize both of the acids? Because the acids are neutral when you hit the end point, the equivalence point. So neutralization has occurred when you hit the equivalence point. Therefore, if it took the same amount of base to neutralize both of them, the concentrations would have been equal. All right, so I have equal concentrations. I can make equal look a little better. There you go. All right, and that's the end.